Hey everyone, and welcome to This Explainer. I am absolutely thrilled to have you here today. If you've ever felt like your control systems were bouncing around just a little too unpredictably, or if you're finally ready to graduate past basic Ziegler-Nichols tuning, well, you are in exactly the right place. Today, we're diving deep into a system identification and controller tuning masterclass. We're going to crack the code on advanced tuning methods together, and I promise, by the end of this, you'll look at step responses in a whole new light. Here is our agenda for today. We'll be covering 1. The CHR tuning method, 2. The Cohen-Coon method, 3. Lambda tuning for PI, 4. Lambda tuning for PID, and finally, 5. Classifying controller design methods. Before we really get going, I want to explicitly mention that this entire comprehensive presentation, this brilliant engineering blueprint we're unpacking today, was prepared by Dr. Nima Madian. He really did the heavy mathematical lifting here, and we just get to act as your guide, breaking down his expert insights one concept at a time. Section 1. The CHR tuning method. Let's start with the Chien, Hrones, Reswick, or CHR method. This is basically designed to be a much more robust alternative to your classic Ziegler-Nichols approach. Built on an integral model with delay, CHR doesn't just lock you into one path. It actually lets you target the fastest possible response with either a strict 0% overshoot or, if you're feeling slightly more aggressive, a 20% overshoot, all depending on your system's tolerance. Okay, when we look at Dr. Madian's parameters for CHR, I know it feels like a lot of math right up front, but just focus on the core takeaway here. This is absolutely crucial. CHR controller values are generally smaller than what you'd get using Ziegler-Nichols. And why does that matter? Well, smaller gains actually lead to a slightly slower but way more expected and stable response. It's really about trading a tiny bit of speed for a whole lot of reliability. Section 2. The Cohen-Coon method. Moving right along, the Cohen-Coon method uses a 3-parameter model, so we're talking gain, time constant, and delay. Now, this method has a highly specific response criterion, which is targeting quarter-cycle behavior. But the real meat here is the ultimate design goal. Cohen-Coon is perfectly optimized for the maximum rejection of input disturbances while simultaneously minimizing integral error. Basically, if your system is constantly getting hit with outside noise or sudden load changes, this is the exact blueprint you want. Now, to translate Dr. Madian's specific controller parameters here, he points out a really critical mathematical relationship regarding the parameter tau. It's super fascinating. For a very small tau, the values behave quite a bit like Ziegler-Nichols, but as tau increases, the required integral time actually decreases, which ultimately gives you a much better, tighter system response. So before the math really ramps up, let's take a quick mental breather and distill what we've learned so far. The philosophical difference is honestly pretty clear. If your priority is the absolute fastest response with controlled overshoot, you're going to reach for the CHR method. On the flip side, if your priority is aggressively rejecting those random disturbances and minimizing that integral error, you lean on the Cohen-Coon method. It's kind of like having two completely different tools for two very different industrial realities. Section 3. Lambda tuning for PI. All right, so what exactly is the core idea of lambda tuning? Dr. Madian spells it out beautifully. Instead of relying on just open-loop trial and error, we are directly placing the dominant closed-loop pole exactly where we want it on the complex plane. We literally just set it at s equals -1 over lambda. That parameter, lambda, basically becomes our magic dial. It directly dictates the desired time constant for the entire closed-loop system. The derivation flow for a PI controller using pole cancellation works by starting off assuming the standard PI structure. From there, it takes us mathematically all the way through the process to generate our closed-loop characteristic equation. To make sure that logic is crystal clear, we can break that whole process down into 4 actionable steps. Step 1. Assume your PI controller. Step 2. Perform pole cancellation by setting the integral time equal to the process time constant. Step 3. Define your open-loop transfer function using a Taylor expansion to handle the delay. And finally, Step 4. Formulate the closed-loop characteristic equation. This sequential flow is really the backbone of the lambda derivation. And here is the payoff for all that work. By placing that dominant pole at -1 over lambda, Dr. Madian derives these incredibly clean final PI parameters. Your integral time simply equals the process time constant. But check out the general conservative rule of thumb here. This is pure gold for field engineers. You basically just select your lambda value to be 3 times your process time constant. That is a super practical takeaway you can use literally today. But wait, we definitely need to pause here for a massive safety warning. Dr. Madian heavily emphasizes this point. You must carefully evaluate your system first, because you should absolutely not use the pole cancellation method for processes with dominant delays. I repeat, if your dead time is significantly larger than your time constant, canceling the stable process pole is just going to lead to sluggish, really poor responses. It is a distinct weakness of this specific derivation. So, what are we supposed to do if we do have a dominant delay? Well, Dr. Madian provides a really robust mathematical alternative, disturbance rejection without pole cancellation. Notice that we don't actually cancel the pole here. Instead, we generate a more complex characteristic equation and match it term by term with a desired ideal characteristic equation. And that yields completely new control coefficients perfectly suited for those tricky dominant delay systems. Section 4, Lambda tuning for PID. Okay. The first hurdle when we scale up to PID is that the math naturally produces what we call an interacting or series form controller. But since most industrial PLCs use the standard PID form, Dr. Madian clearly maps out the exact conversion standard. He provides the algebraic translations needed to turn those interacting values into your standard K, Ti, and Td parameters. Now, dealing with a derivative term alongside the system's time delay gets pretty complex, but Dr. Madian uses a brilliant mathematical trick here, the PID approximation. This approximation basically converts that problematic exponential delayed term into a nice, clean, rational polynomial fraction. It's a total game changer, and it's the key that unlocks the rest of the derivation so we can build a clean characteristic equation. Let's translate that advanced math into a clear sequence so you can track the engineering logic. Step 1, apply the PID approximation for the delay. Step 2, assume equal time constants to cancel process poles. Step 3, define your new open loop function. And step 4, formulate the characteristic equation. It's exactly the same rigorous, logical flow we just used for the PI controller, just upgraded for the extra complexities of PID. Which brings us to Dr. Madian's ultimate goal for this section. By substituting our dominant pole back in at s equals -1 over lambda and using those interacting conversion relations we talked about earlier, we arrive at these beautiful standard PID controller coefficients. You now have explicit formulas for your tuning parameters strictly based on your system model and your chosen lambda value. Section 5, Classifying Controller Design Methods. To wrap things up, Dr. Madian classifies all these design methods so we can perfectly contrast them. On one side, we have open-loop quantitative criteria. This includes the CHR and Cohen-Coon methods. They review closed-loop quality, sure, but they're tuned purely via open-loop parameters. On the other side, we have closed-loop pole placement criteria, championed by the Lambda tuning method, where we directly engineer a very specific time constant. But the coolest takeaway is that both categories are mathematically optimized for practical, real-world implementation. So, we've walked through the math, we've seen the derivations, and we've classified the tools from Dr. Madian's masterclass. The only question left is for you. How will you take these dense mathematical blueprints off the screen and apply them in the field? Next time you're staring down an unruly process, which tool are you going to reach for? Thank you so much for joining me in this explainer. Keep exploring, and I'll catch you in the next one.